Okay, hello guys. Let us now continue with our discussion. So in our last video, we have discussed about sets. Then we also have discussed about the relations, then special kind of relations called the function. Let us now continue with our discussion about functions. We have special types of functions. Some functions do have this property, some don't. Okay, so we define a function phi mapping x to y is called 1 to 1 if phi of x sub 1 is if phi of x sub 1 equals phi of x sub 2 only when x sub 1 is equal to x sub 2. Meaning, if the images of x sub 1 and x sub 2 are the same, then it should follow that they are the same. Okay? So this would be our convention of proving that a function is 1 to 1. Next, we have the function phi is onto y if the range of phi is y itself. Meaning, if phi pairs the domain x into whole of y. In other words, all elements in y are taken as images. Now, some other terms that can be used to these properties are injection, surjection, and bijection. A function which is 1 to 1 is said to be an injection. A function which is onto is also called a surjection. And a function which is both 1 to 1 and onto is what we call a bijection. Okay, let me now demonstrate how we use this definition in proving that a function is 1 to 1 and onto. Okay, take for example the function, say g, mapping the set of real numbers to the set of real numbers. Take note that the domain here is the set of real numbers. The codomain is the same set of real numbers. Defined by the equation g of x is equal to, let's say, 5x minus 1. Okay. So, let us verify 1 to 1-ness. Pardon me for the penmanship. Okay. So, in proving 1 to 1-ness, again, if we would go back to the definition, we would say that the function is 1 to 1 if the image of x sub 1 equals the image of x sub 2 should imply that x sub 1 is the same as x sub 2. That is, if their images are the same. Meaning, a necessary condition should be that they have the same images. So in our proof, we should assume that there are two elements with the same images. So, say, x sub 1 and x sub 2 have the same images. That is, suppose, excuse me. So, suppose x sub 1 and x sub 2 have the same images. That is, g of x sub 1 is the same as G of x sub 2. Okay. Now, since G is defined by the equation G of x equals 5x minus 1, so if the element here is x sub 1, then its image would be 5x sub 1 minus 1. So, it should follow that the image of x sub 1, that is 5x sub 1 minus 1, is equal to the image of x sub 2. So that would be 5x sub 2 minus 1. Okay? Let us first go up. Okay. Now, since we are dealing with whole numbers, the properties of whole numbers should be satisfied by these elements. Okay, meaning all properties of real numbers can be applied here. So therefore, we can apply addition property of equality. Meaning, we can add the same number to both sides of the equality, the equation. Okay, so if we add 1 to both sides, so we say plus 1 here, plus 1, then add also 1 here. It's not minus. Again, imagine adding 1 here. So this would be negative 1 plus 1, 0. Negative 1 plus 1, 0. 0 plus 5x sub 1 would be 5x sub 1 equals 0 plus 5x sub 2 would be 5x sub 2. Okay. And then, we can multiply both sides of this equality by the reciprocal of 5. That is 1/5. Multiply this by 1/5. Also multiply this by 1/5. We would have 5 over 5 x sub 1 equals 5 over 5 x sub 2. Which would give x sub 1 equals x sub 2. So we see that if it so happens that g of x sub 1 is equal to g of x sub 2, it would follow that x sub 1 equals x sub 2. Therefore, we say that g is 1, 2, 1. Okay? Now for the ontoness. Let us go back to the definition. The definition of onto function asserts that a function is onto if the range of the function is the codomain itself. The range of the function is the codomain itself. Meaning, all elements of the codomain is an image of some element in the domain. So if we would look that at in a diagram form, so this is, let's say, R contains the set. This is the set of all whole numbers. I mean real numbers, and this is the same set. This is also R. All of these elements here should be paired with some elements here. So each element is in the codomain should be an image of some element here. Meaning, if you have an element here y, there is y there, there should be some x here, x which is an element of R, which pairs to y. You follow? So again, if there is an element in the codomain, there must be an element in the domain for which y is the image. So that we can say that all elements in R in the codomain are images. Okay? Nahurot og kapares ang mga elements sa codomain. So, let us proceed. So again, remember that G maps R to R. So all elements here, if we are to prove that G is onto, we should prove that all elements here are images of elements here. So let's say there is an element here Y. So we say Y, let Y be an element of the codomain. Be an element of the codomain R. Okay, so Y is a real number. So we'll try to find a number X, and it should be in the domain. What again is the domain? R, real numbers. Okay, we need to find this number in this set in R such that the image of X under the function G, that is G of X, is Y. Okay, so we need to find what is this X so that its image is Y. Take note, Y is known. Okay, Y is already there. We'll have to look for X. Okay, if we know what Y is. Now, by the definition of the function, G of X is equal to X minus 1. Therefore, since G of X equals Y, so it should follow that 5X minus 1 equals Y. But take note that we are looking for X, and we already know what Y is. Y is a real number. So we need to find an equation isolating X of the rest. So we can add both sides by 1. So we have 5X equals Y plus 1. And then, since 5 is positive, there should be a reciprocal of 5. So 1/5. We multiply both sides by 1/5. We shall have X is equal to Y plus 1 all over 5. But take note that Y is a real number. So Y plus 1 must also be a real number. But a real number divided by 5 is still a real number. Meaning, X here with the value Y plus 1 equals 5 is a real number. Meaning, we can always find a real number X for every real number Y. In other words, if Y is an image, its pre-image would be in the form Y plus 1 equal all over 5. So if we need to show that, we see that G of X would be G of Y plus 1 over 5 So by definition, that is 5 times y plus 1 over 5 minus 1. And then 5 over 5 is 1 times y plus 1 will just be y plus 1. Then bring down minus 1. 1 minus 1 is 0. Y plus 0 is y. So we see that if x is this value, then its image would be y. Meaning whatever y is, there is always an element in the domain for which y is the image. Therefore, G is onto. Okay, we're done. Let's now move on to the next. Now, if phi is a one-to-one function, meaning one element in the domain is being paired with exactly one element in the codomain, and each element in each image has only one image. Let me illustrate that using a diagram. So this is our domain X, and this is the codomain Y. Suppose there are elements in X here, and there are elements in Y. Let's change the color. So say Y has red. Red elements. And there is a one-to-one function from X to Y. Let us make this a bit larger. Now, suppose there is a function pairing elements of X to Y. So let's say this element is being paired with this. This element is being paired with this one. This element is paired with this. And this element is paired with this one. This element is paired with this one. Okay. Now, we see that each element in Y was paired with exactly one element in X. So we see that this is a one-to-one function. So there is a one-to-one correspondence between the elements of the domain and the elements of the codomain. Meaning, if we would reverse the process and we take Y as the domain and X as the codomain, we would have, if the correspondence would still be a function, since each element in Y would be taken as a pre-image and each would have a unique image in the codomain, which is this time X. Meaning if the direction would be that way, and this would be the domain, so the correspondence from here to here would still be a function. We call that correspondence as the inverse function. That is, if, let's say, if the correspondence from here to here is red, and let us we call that as phi, there would also be a function in the blue direction, and that would be called phi inverse. And that is the notion of inverse functions. Okay, so we define formally as follows. Okay, so if a subset of x cross y is a one-to-one function phi mapping x onto y, then each element x in x, capital X, appears as the first member of exactly one ordered pair in phi, and also each element y in capital Y appears as the second member of exactly one ordered pair in phi. Thus, if we interchange the first and the second members of all ordered pairs x, y in phi to obtain a set of ordered pairs y, x, we get a subset of the cross product capital Y cross X, which would also give a one-to-one function pairing Y onto X. So we would call that the inverse function of phi. We denote that by phi inverse. The superscript -1 here is not an exponent but a symbol for the inverse of the function. Okay? So in other words, if phi maps x one-to-one onto y and phi of x equals y, then phi inverse maps y on one-to-one onto x, and the image of y would be x under phi inverse. Okay, let us go back to the notion of cardinality. I've said earlier that cardinality is just another term for the number of elements. If two sets have the same number of elements, they would have the same cardinality. But here is the formal definition of sets having the same cardinality. Two sets x and y have the same cardinality if there exists a one-to-one function mapping x onto y. That is, there exists a one-to-one correspondence between x and y. Okay, let us go back a bit, and let's go back to the preceding page. Okay, in the preceding page, you would see that the set of positive integers is being paired with the set of integers. Suppose 0 in the set of integers is paired with 1, -1 is paired with 2, and +1 is paired with 3. Then -2 is paired with 4, +2 is paired with 5. -3 is paired with 6, +3 is paired with 7, following the same process. Meaning, each integer would be paired with exactly one positive integer. And there would be no duplication. No duplication. All integers would be paired with a unique positive integer. In other words, there would be a one-to-one correspondence between the set of integers and the set of positive integers. So there is a function pairing the set of integers one-to-one onto the set of positive integers. So by definition, therefore, of sets having the same cardinality, we would say that Z has the same cardinality as positive integer z plus. Okay? They would have the same number of elements. Why? Because they are both infinite and we can pair them one to one onto one another. So it is fascinating that it is possible therefore for a subset to have the same cardinality as its superset, just like what happened in Z and Z plus. Okay, here is an example showing when one-to-one and onto are not satisfied. For example, we have here the function defined by function f mapping real numbers to itself, defined by the equation f of x equals x squared. It is said here that it is not one-to-one. Why? Because 2 and negative 2 would have the same image. F of 2 would be 2 squared, which is 4. F of negative 2 would be the square of negative 2, which is also 4. Meaning they have the same images, but these two elements are not the same element in the domain. So the function is not one-to-one. Also, it is not onto. Why? Because take note that the codomain is R, but not all R are images. Take for example negative 2. We cannot find an element here, an element of R. We cannot find a real number for which the square is negative 2. Okay? Therefore, there is no pre-image for negative 2. Hence, negative 2 is not an image. It is not included in the range. The range would be just a subset of R and not R itself. Therefore, F here is not onto. Okay? However, it can be proven that the function g mapping R to R defined by g of x equals x cubed can be proven to be one-to-one and onto. You can verify that yourselves. Next, let us talk about partitions and equivalence relations. Okay, let us first talk about the notion of disjoint. Two sets are said to be disjoint if they don't have any element in common, if they don't have any intersection. Okay? So I believe you know that in your set theory. Why did we mention disjoint? Because such concept is used in the concept of partition. We define a partition of a set S as a collection of non-empty subsets of S such that every element in S is in exactly one of the subsets. The subsets are called the cells of the partition. Okay? There should be a subset for each element in S, and then each subset would be non-empty, and each element should be in exactly one of the subsets, meaning no subsets would have the same element, meaning each subset would be disjoint from the rest. Okay, to illustrate that, let me show you an example. So take for example a set S containing elements 1, 2, 3, 4, and 5. If we are to take a partition P of S, and we want that partition to have, let's say, 3 cells, meaning we would subdivide the elements of S into 3 cells. So I have made 3 brackets, 3 pairs of brackets. Let me get this a little bit better. Okay, so we have 1, 2, 3 cells. 3 cells. So again, each element of S should be in exactly one of these 3. For example, we put 1 here. We put 1 there. 1 cannot be in the other 2. If we put 2 here, then 2 cannot be found in the other 2. If we put 4 here, 4 cannot be in this 2. If we put 3 here, 3 cannot be here in this 2. And if we put 5 here, 5 cannot be found in this 2. So notice that these 3 cells are disjoint. All elements in S have been included in exactly one of the 3 sets, subsets of S, or we call this cells of S. So that is how partition works. Okay. Take here this for example. By the way, we shall take this symbol to denote the cells. This symbol here. Sorry, that's too thick. This symbol here. This symbol here denotes the cell that contains the element X. Okay? So, in our earlier example, this is the cell containing 3 and 5, meaning that can be denoted as 3 bar or 5 bar. So 3 bar again is the cell containing 3. So that would be the cell containing 3 and 5. And the same is true for 5 bar. This is 2 bar or also known as 4 bar. And this is 1 bar. Okay? I hope you were able to follow. So, for example, if we are to consider the set of positive integers, z plus, and then split the set into 2 subsets, one having positive even integers, meaning those that can be divided by 2, and the subset containing the odd positive integers. That would be those which would leave a remainder 1 when divided by 2. Okay, for example, 3, 5, 1, 7, and so on. Then we would obtain 2 cells. One of the cell would contain 14. The cell that would contain 14 would be the set of even positive integers. So we say that 14 bar would be the cell containing 2, 4, 6, 8, 10, 12, 14, 16, 18, and so on. Okay, the other would be the cell containing 1. It would contain the elements 1, 3, 5, 7, 9, 11, and so on. Okay, also we could partition the set of positive integers into 3 cells. First, the cell that contains integers exactly divisible by 3. Then those that would leave a remainder 1 when divided by 3, and those that would leave a remainder 2 when divided by 3. Okay? Let me illustrate that for you. So we have positive integers. We can we can partition this set by considering what would be its remainder when divided by 3. So, first, those that will give a remainder 0. Those would be 3, 6, so what else? 9, 12, and so on. So this would be the cell containing 3. Another cell would be the cell containing 2, which would give a remainder of 2 when divided by 3. So this would have the elements 2. What else? 5. Because the remainder would be 2 when you divide 5 by 3. What else? 8. Then you have 11. And so on. And lastly, those that would give a remainder of 1. That would be the cell that would contain 1. So that there will be 1 because 1 divided by 3 is 0, remainder 1. So the remainder is 1. Then we have 4. Then we have 7. Oh, sorry. Then you have 10. And so on. So notice that all elements in Z plus have been accounted for. Diba? You have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 13 would be here, 14, 15, 16, and so on. Meaning we are able to partition Z plus into 3 cells by considering the process of dividing the integer, the positive integer by 3 and take the remainder. Okay? So this, the cells are what we call the residue classes. So this here therefore is the residue class containing 3. This is the residue class containing 2. And this is the residue class containing 1. Residue pertaining to the remainder. Okay, what remains? The residue. Okay. Then the divisor is what we call the modulo. So in general, we would say that for each positive integer 3, n, for each positive integer n, we take n as our divisor. We can partition z plus, or the set of positive integers, into n cells. Take note, if the divisor is 2, there would be 2 cells that would contain even, and those that would contain odd. If the divisor is 3, there would be 3 cells. 1, those whose remainders is 1. Second, those whose remainders is 2. And lastly, those with remainders 0. Therefore, if the divisor is n, there would be n cells. Okay, so according to whether the remainder is 0, 1, 2, and so on, up to n minus 1. So these are what we call the residue classes modulo n in the set Z plus. Okay. Next, recall the concept of equivalence relation. So, again, an equivalence relation is defined to be a relation which is symmetric, reflexive, and transitive. So, a relation is symmetric if each element is related to itself. Okay? If each element is related to itself, then the relation is said to be symmetric. The relation is said to be, reflexive rather. Reflexive. The relation is said to be symmetric if it so happens that x is related to y, it should follow that y is also related to x. Okay, so that is the property of symmetry. And then the relation is called transitive if it so happens that x is related to y and at the same time y is also related to z, it should follow that x is related to z. If such is true, then we say that the relation R is transitive. Okay? Notice that the relation of equality is an equivalence relation. Why? So we assert that equality is an equivalence relation. Why? Because x is equal to x for all real number x, meaning equality is reflexive. Also, if a number x is equal to y, it should follow that y is equal to x. That is, the relation equality is symmetric. This is true for all real number x and y. We call that the symmetric property of equality. Also, we have the transitive property of equality. Diba? If x equals y and at the same time y is equal to z, it should follow that x is equal to z for whatever elements x, y, and z there are. Therefore, equality indeed is an equivalence relation. That simply follows from the properties of equality. Okay, so where are we? Okay, so we have here another example. We define the relation called congruence modulo n. Let n be a positive integer. an equivalence relation on Z plus corresponding to the partition of Z plus into residue classes modulo n, we discussed in the preceding example, is what we call congruence modulo n, sometimes denoted by this symbol, 3 bars with a subscript n. Rather, we write A is congruent to B modulo n. Then we usually write this symbol. A is congruent to B modulo n. Okay? So, for example, here, in our preceding example, take note here that we considered 3 as the divisor. So, n here, n was 3. So, we see that if n is 3, 3, 6, 9 would be in the same cell. 2, 5, 8, 11 would be the same cell. 1, 3, 1, 4, 7, 10 would be in the same cell. So, we say that, say, 9 and 12 are congruent modulo. How's that? 9 and 12 are to save space. Again, this here is 3. Don't mistake this to 7, because that might look like 7 for you. This here is 3. Okay, so by definition, we say that 9 and 12 are congruent modulo 3. Or in symbols, similarly, we can write that as said earlier, we can write that as 9 is congruent to 12 modulo 3. Also, we see that 7 is congruent to 10 modulo 3. Okay? 8 and 11 are congruent modulo 3. 8 is congruent to 11 modulo 3. Okay? So that is what we meant by congruence modulo n. But if we would go back, try to go back, why are 3 and 6 on the same cell? Why are 3 and 6 in the same cell? Because they gave the same remainder when divided by 3, and that is 0. Also, why are 5 and 8 in the same cell? Because again, they yielded the same remainder when divided by 3. Meaning, two positive integers will be in the same cell if they have the same remainder when divided by 3. Or in general, two positive integers would be congruent modulo n if they would yield the same remainder when divided by n. Okay? So you can simply rewind if you did not get that. Again, if they would yield the same remainder, they would be congruent. Modulo n. N is the divisor, the positive integer considered as the divisor. Okay, so we see here that, for example, we have 15 is congruent to 27 modulo 4. Why? Because if you divide 15 by 4, the remainder is 3. 27 divided by 4 is also 27 divided by 4 is 6. 6, remainder 3. So they share the same, they yield the same remainder. Okay, which is 3. So they are congruent modulo 4. Meaning those numbers with the same remainder divided by a same divisor would be congruent. Modulo the divisor. Okay. Next example. A relation R on Z, on a set Z, defined by N is related to M if and only if the product N times M is greater than or equal to 0. Let us determine whether or not R is an equivalence relation. Okay. So we have here a different definition of a relation. Two numbers are related. If we would reword this, two integers rather. Two integers are related if and only if their product is not negative. See that? Let me highlight that for you. Take note that the set is Z, positive integers, and they would be related if and only if their product is non-negative. If the product of two numbers, two integers are non-negative, they are related. That is what we meant by this example. Okay? That is the definition of R in this particular example. R can be defined differently in some other examples. But in this example, that is how we define R. Two integers are related if their product is non-negative. Okay? Let us now verify the reflexivity. Is any integer related to itself? Number to itself. Is the product of the number and itself non-negative? That is the question. But then, if you consider the square of an integer, there is no such thing as a negative square of an integer. Okay? There is not even a negative square of a real number. How much more for integers? So if you take any integer and square it, the product would always be non-negative. So, since a squared or a times a is not negative, it's greater than or equal to 0, then we say that a is related to a. And that is true for all integers, for all elements in Z. Therefore, the relation R in this case is reflexive, since any element is related to itself. Next, symmetric. Suppose it so happened that A is related to B. Will it follow that B is related to A? If the answer is yes, then the relation is symmetric. Let us see. If A is related to B, then by definition, by how we defined R in this equation, in this example, A is related to B, it would follow that their product is non-negative. So if A is related to B, then A times B is greater than or equal to 0. But then if this is true, if A times B is greater than or equal to 0, it should also follow that B times A is greater than or equal to 0 because it is the same product. B times A is just the same as A times B. So if A times B is greater than or equal to 0, it should follow that B times A is also equal to 0. But then, if the product B times A is greater than or equal to 0, then by definition of R earlier, it should follow that B is related to A. In other words, if we would sum this up, if it so happened that A is related to B, then it would follow that B is related to A. So, the relation therefore is symmetric. Transitivity. So, for transitivity, there would be two assumptions. Suppose A is related to B and B is related to another element C. We should verify whether or not it should follow that A would be related to the third element C. Okay? But, if A is related to B, by definition of R, by how we define the relation earlier, it should follow that the product A times B is non-negative. Also, B related to C would imply that the product also B times C is not negative. Now, A times B is not negative. B times C is also not negative. So, if we multiply these two numbers here, AB and BC, since both of them are non-negative, their product should also be non-negative. Do you follow? Their product would also be non-negative, meaning AB times BC, that is AB squared C, which is the same as ACB squared, would be non-negative. But, if only we knew that B squared is not 0, if B squared is positive, then we can divide both sides by B squared, resulting to AC greater than or equal to 0. But we are not sure of that. It was not assumed that the element B is greater than the element B squared is greater than or equal to 0, because B squared can be 0 if B is 0. So it is not always the case that the square of an integer is positive. It could be 0 when B is 0. But B, again, can assume integer, so B can be 0. So it is possible that B is 0. Meaning, not at all times that it should follow that A is related to C. Meaning, it cannot be proven that the relation is transitive. If that happens, that you cannot prove a conjecture and you think that it is false, what you would do is to disprove. We disprove by showing a particular case wherein the statement which we want to prove is not true. We call that a counter example. Okay? So here, it is taken into a particular case wherein the first element is 3, a negative 3, the second is 0, the third is 5. So, it is true that negative 3 is related to 0 because the product is 0, which is not negative. Meaning it is true that negative 3 is related to 0. It is also true that 0 is related to 5 because the product of 0 and 5 is 0, which is not negative. But, negative 3 times 5 is negative 15, which is this time not greater than or equal to 0. Meaning, negative 3 is not related to 5. So, it is not, the relation is not transitive. Let me just show that to you formally. The counter example shown here. again, negative 3 is related to 0. Why? Since negative 3 times 0 is equal to 0. Okay? And 0 is equal to 0. Okay? Also, take note ha, A is related to B if and only if the product A times B is greater than or equal to 0. Meaning, if the product is greater than 0, related. If the product is 0, related. But the product of these two is 0, meaning they are related. Also, 0 is related to 5. Why? Because 0 times 5 is 0. It falls in the second condition, equal to 0. That would mean, indeed, 0 is related to 5. But negative 3 times 5 is negative 15, which is neither greater nor equal to 0. Okay? Not one of the two conditions is satisfied. Meaning, negative 3 is not related to 5. Even if negative 3 is related to 0 and 0 is related to 5. Therefore, the relation defined is not transitive. Meaning, the relation is not an equivalence relation because one of the properties was not satisfied. Okay? Oops, sorry. Here we have our first theorem of the subject stating that let S be a non-empty set and this symbol be an equivalence relation on S. Okay? That is the similar symbol. See that? But that doesn't mean similarity in this context. Just an arbitrary relation. And assume that it is an equivalence relation on the set S. Then, as asserted, the relation would yield a partition of S, wherein the cell containing A would consist of all those elements in S which are related to A. So, the cell containing A is the set of all elements X in S such that X is related to A. Okay. Mo partition kuno ang equivalence relation. Unsaon ni sa pagpartition, unsaon sa pagbuwag-buwag. Kadtong related sa usag-usa, mapareha silag cell, mag-uban silag cell. Okay, ang usa ka equivalence relation kuno makapahimog partition. Okay, let us now see the proof. Okay. Also, in addition, each partition of S gives rise to an equivalency relation. Okay? Kung na-partition, makahimo po ka o equivalency relation. So, duhay assertion. Ang equivalency relation, mo partition. In addition, ang partition, makahimog equivalence relation. Okay? Sige. Let us discuss the proof. We must show that the different cells A bar with that definition stated earlier for an element A in S do indeed give a partition. If we would go back to the definition of partition, it is said that a partition should have non-empty subsets of S wherein each element of the set S would be contained in exactly one of the cells. Okay? So, let us verify that. Tinuod ba nga mabuwag-buwag ang S into cells and then each element of S mabilong og exactly usara ka cell. Okay. And then, it should be disjoint. Meaning, if A belongs to the cell containing B, then the cell containing B is the same as the cell containing A. Meaning, two different cells cannot have the same element. If they have the same element, then they are the same cell. Okay? So, mga naibut pa sa botani. Let A be an element of S. Then, A would be found in the cell containing A. Okay? Why? Because the relation is reflexive. Diba? Kaya the relation is an equivalence relation, so reflexive. Meaning, every element is related to itself. So, ang A related sa A, meaning, tuas siya sa cell nga nag-contain sa A. So, it belongs to one of the cells. Okay, so A therefore is in at least one cell. Suppose there is another cell that contains A. Okay, napailain. Gawas kay exactly one cell man, meaning at least one and at the same time at most one. So, okay na ang at least one. Suppose dili at most one. Napailain. Suppose there is another cell that contains A. Let's say, let's call that cell containing B or B bar. We need to show that A bar is just the same as B bar. But, A is in B bar if A is related to B. But, if A is related to B, since the relation is an equivalence relation, meaning it is symmetric, it would follow that B is also related to A. Meaning, B is in the same cell as A, or it is in the cell containing A. Okay? Now, we show that these two sets are equal. The convention is to show that one is a subset of the other and vice versa. So, each set is a subset of the other. So, first show that the cell containing A is a subset of the cell containing B. To do that, let us show that every element in A, in the cell containing A, is in the cell containing B. So, let X be an element of the cell containing A. But, if X is in the cell containing A, it would follow that X is related to A, but by definition. But, A is in the cell containing B, meaning A is related to B, by definition again of the relation. But, X X is related to A and A is related to B. The relation is a transitive, is an equivalence relation. So it is transitive. So it should follow that X is related to B. Here, X is related to B. Meaning, X is also in the cell containing B. But in our assumption, X is in the cell containing A, and it followed that X is in the cell containing B. Therefore, the cell containing A is a subset of the cell containing B. Now, suppose there is another element, Y, in the cell containing B. Then, Y should be, again, related to B. But again, by our assumption, A is in the cell containing B, so A is related to B. By symmetry, B is related to A. Then Y is related to B and B is related to A. So by transitivity of the relation, it would follow that Y is related to A, meaning Y can also be found in the cell containing A. But Y was assumed to be in the cell containing B. Therefore, the cell containing B is a subset of the cell containing A. Since the cell containing A and the cell containing B are subsets of one another, so we say that B is just, the cell containing B is just equal to the cell containing A. Meaning, there can only be one cell that can contain A. So, every element in S is in exactly one cell. Okay, so we have shown that an equivalence relation would result to a partition. Also, a partition would result to an equivalence relation. When we define a relation to be two elements are related when they belong to the same cell. Okay? Since an element belongs to the same element as itself, meaning the relation is reflexive. Since also, if an element is related, it belongs to the same cell as B, if an element A belongs to the same cell containing B, then B is in the same cell containing A, because that is a partition, meaning that relation would be symmetric. If A is in the same cell as B, and B is in the same cell as C, that would mean that A is the same cell as C, because a partition is disjoint, meaning the relation of being in the same cell would be is transitive. Since that relation is both or all of the three, reflexive, symmetric, and transitive, then the relation of being in the same cell in a partition is an equivalence relation. Okay, so that would be all for this second part of our discussion, the first topics. We would just discuss the next part of lesson 1 in our next video. You may want to hit the subscribe and the bell button for you to get notified whenever I have uploaded the video, the instructional video for our topics. Okay, thank you for listening and bye.